So this is regarding, right, we were talking about how to enhance the sensitivity in terms of measurement, right, technique, the absorption measurement technique, what we have now, right, discussing what we are discussing, how to enhance the right sensitivity. So basically sensitivity in this such measurements where we are trying to measure trace gases, very small concentrations of various types of gases, then in such case the absorption, right, the input intensity and the output transmitted intensity, both of them are comparable, very difficult to distinguish, right, the concentration so easily. So is to improve that, what we thought, if we can increase the path length. So by increasing the path length, we improve the sensitivity in measurements. The path length can be improved by multi-pass cells such as this used here, or by inserting a sample cell within the laser cavity, okay, and the wavelength of the laser will be matched to the absorption band. So it indirectly increases the path length, isn't it, because it is within the laser cavity, multiple passes will happen, that improves the path length. Okay. Now there is one more technique which is known as cavity ring down spectroscopy, okay, and this technique allows multi-pass, right, such measurements, and not based on the intensity of the light, okay. Change, see, basically in absorption we captured that change in input and output intensity, we take that information and capture the absorption, right, or cross or the concentration of molecules present, etc. However, in cavity ring down spectroscopy, it is based on the temporal, right, characteristics of the output pulse. Okay. So what it is, so basically in cavity ring down spectroscopy, there are, let us say the cavity is made using two such, right, mirrors, let us say with reflectivity R1 with reflectivity R2, which is very high. Okay. So when any let us say a laser beam with a pulse laser beam, okay, with a wavelength lambda, the wavelength lambda is matching with the absorption, right, by the molecules which are present in this, okay, trace molecules which are present. Okay. Now when this light passes through this cavity, the cavity configuration is such that this length is n lambda by 2, where n is an integer. So what it means, right, integer, okay, that means it is a standing wave cavity, it allows, right, multiple, right, reflections, okay. So light will pass through, it will reflect back, so constructively it will, right, it will not get lost easily, except that every end mirror ends, let us say this reflectivity is very high, okay, very high, R1 is very high, R2 is such that some small transmission is taking place. So what will happen, even if R1 and R2 are equal, where right, some transmission on either end can take place. So if I am sending a pulse, okay, with time t and intensity lambda is varying, okay. So I am sending a pulse fly, what we will see here as the transmission, right, characteristics with time is, right, intensity of the transmitted light now, okay, transmitted light now will be something like, it will be large, okay, initially, but slowly every round trip it will decrease, okay. So let us say pulse output comes out, okay, and then part of that, because of the high reflectivity, most of the light will get reflected, only small amount of light gets transmitted, Okay. Then again second pass, again some part of the light will get transmitted, and right, the other part, remaining part will get reflected. Every reflection there are some losses. The losses are due to absorption and due to the transmission at these two mirrors R1 and R2. Hence, every reflection right will end up with if there are no molecules present, every reflection the losses are due to the transmission characteristics of R2 mirrors. So, you will see that as with time the pulse, one single pulse will have such, right, transmission characteristics. Okay. Input pulse is single input pulse and output is right, is basically something like an exponential decay. Okay. And now, if I introduce gas molecules and then absorption also comes into picture, in that case now the intensity, change in intensity or change in the transmission intensity with every pass, okay, will be again different. Okay. Why is it different? Because of the absorption coming into picture, isn't it? Previously, if there are no molecules, the without no molecules, no presence, okay, no absorption at all, correct? No absorption, okay, right, because no such molecules which will absorb the incoming light is present. In that case, the decay characteristics, okay, is shown like this. Okay. The output intensity decay characteristics, okay, and in the presence of absorbing molecules, right, in the presence of absorption. Right, because the absorbing molecules, right, what will happen? Because of the increase in losses, the transmission characteristics will decrease, will be different. So, now by measuring the lifetime, right, in the cavity, we can estimate some parameters such as concentration. So, lifetime, how do we estimate in exponential decay? The lifetime can be captured as I transmission lambda is I at this point, right, at this point, let us say IT at 0, right, at lambda exponent of minus t by tau, okay, where tau is the lifetime of this cavity, right, and this tau, when intensity of transmitted intensity becomes 1 by E of its initial this intensity I 0 or T 0 lambda, where T equal to 0 lambda, then we will get tau as the cavity lifetime. Okay. And in the presence of absorbing molecules, this cavity lifetime will decrease. Okay. T is the cavity lifetime where the transmitted intensity at any point T becomes 1 by E times T equal to 0, intensity at T equal to 0. Is it okay? So, this is the idea. Now, in terms of some simple equations, in order to derive this lifetime value, okay, this lifetime, what shall we do? So, we will just quickly try to derive. So, I will give you some basic approach, okay, and then we will correlate it with this measurement approach, okay, cavity ring down spectroscopy measurement approach. So, so is to give you let us say consider a resonator, okay, with right a resonator with right reflectivity R1, R2, okay, and resonator means length of this resonator will be equal to n times lambda by 2, it will form a standing wave pattern. Okay. Now, consider that let us say inside this resonator, let us say initially at t equal to 0, that is energy U is the energy inside this cavity. Okay, U, 1 minute, okay, energy density U. Okay, so at t equal to 0, let us say, okay, so that is right. See, at t equal to 0, energy density is U. Okay, so after one round trip, okay, so one round trip, right, after one round trip, let us say this, after one round trip, okay, after a round trip, first one round trip. So how do we estimate round trip? Round trip time, let us say t is equal to, let us say cavity length is L, speed of light in this cavity is c, so it will be 2L by c, correct, right, round trip. After round trip, let us say u will become VU. Okay, VU. What is V? V is a loss factor. Okay, V is a loss factor, and right. So because of some loss, right, due to this, right, at the reflector ends, etc. Now, in the after one round trip, the amount of energy density which is in this cavity is VU. Okay, so if V, right, say if V is equal to 1, means there is no loss, correct, there is no loss, correct, right. If V is equal to 1, after one round trip U remains U, so there is no loss. Okay, and when V is less than 1, there is a loss, correct, there is a loss. Okay, so after second round trip, it will become V square U, correct, V square U, and it will keep on accordingly, right, changing. Now what I am trying to build, that let us say at so let us say at t equal to 0, at t equal to 0, let us say intensity is I0. Okay, energy density, okay, in terms of energy density, let me, I think this, okay, energy density is, let us say Z0. Okay, energy density inside the cavity is, okay, Z0. Okay, so at t equal to 0, time t equal to 0, and after a round trip, okay, after a round trip, it will become, right, after a round trip, that means t equal to t, right, t equal to t, Z will become V into Z0. Okay, so after S number of round trips, after S number of round trips, okay, where t equal to S time t, correct, S times t, right. So Z at S, okay, here at round, after a round trip, so Z at t, Z at S will be equal to V raised to S into Z0, isn't it? Okay, and so in general Z at t can be written as Z0 V raised to t divided by t, right. How many number of round trips will determine the total, right, loss. Okay. Okay. So now we know the identity that a raised to x can be written as e raised to x natural log of a. Okay. So like this we can write. So zt can be written as z0 e raised to minus t into log of v divided by t. Okay. So, z is equal to z0 e raised to minus t divided by tau p, where tau p, which is nothing, sorry, where tau p, okay, tau p is t divided by minus log of v, correct. If I compare this equations, lifetime within the cavity is given by this form, okay. T is the round trip time, V is the loss factor, okay. So, if the loss factor is 0, is 1 maximum, lifetime will be infinite, okay. There is no decay theoretically, okay. And if there is a loss factor V coming into picture which is less than 1, automatically the lifetime is estimated, okay, based on this, okay. Now, if I compare this losses with our mirrors etc. coming into picture. So, let us say there is a mirror and there is some loss due to absorption, correct, and scattering etc., but absorption. So, mirror with reflectivity R1, another mirror with reflectivity R2, and the loss per cavity round trip, okay, alpha cavity, it is known as round trip loss, okay, round trip, not round trip, per trip, okay, not round trip, per unit length, okay. So, alpha cavity is loss per right, alpha cavity will be equal to, 1 minute, minus alpha, right, alpha cavity is a loss in one single way. So, not in terms of round trip loss, it is cavity loss in one trip, okay, not one trip, but one way, okay, one way cavity loss, okay. So, it is right, if the length of the cavity is L, then alpha of the cavity is nothing but alpha into L, okay, alpha of the cavity is alpha, and if the length is L, okay, what is alpha? It is loss per distance, right, loss coefficient, unit is per centimeter, correct, per length, unit length per centimeter, okay, that is the length, okay. So, that is alpha, while alpha of the cavity is alpha into L, where L is the length of the cavity, okay. Now, if we express this losses R1 at mirror and R2, another mirror R2 and alpha of the cavity, V is nothing but R1 R2 1 minus alpha square, okay, 1 minus alpha of the cavity, okay, alpha cavity square, okay. So, this will be the V factor, okay. So, if R1 is 1, 100% reflection, R2 is 1 and there is no loss in the cavity. So, 1 minus alpha is also 1. So, V is equal to 1, correct, V is 1, no losses in the cavity. So, this, and if there is a loss due to partial reflection and partial transmission etc., this is the V factor, okay. So, if R1 is small or transmission is coming into picture, automatically V will come into picture less than 1 factor, okay. So, if I substitute this part in tau p, so tau p is nothing but t divided by minus log of V, or instead of this we can write t is nothing but 2L by C round trip, right, in the bracket minus natural log of R1 R2 minus natural log of 1 minus alpha of the cavity square, right? Same, right? I can use this this form and using this form, right, substituting in place of v as this form and simplifying, we will end up with this outcome. Okay, this. Okay, so indirectly now if let us say R1 equal to R2, which is R, okay, then I can also express this in terms of R1 R2 as equal to R square, correct, that is yes. Now one more thing, that when R is approximately 1, okay, very nearer to 1, okay, very nearer, but less than 1, but very nearer to 1, okay, and alpha of the cavity is right much, so absorption loss, okay, is much less than 1, okay, much smaller, very small value of alpha if we consider, then natural log of R can be given as 1 minus R and natural log of 1 minus alpha can be given as alpha, okay. So you remember, okay, this you can find out from the mathematics, this thing, okay, when R is very nearer to 1, okay, and when alpha is less than 1, then so if I make use of this, right, 1 to this and try to derive tau p, then tau p will be equal to 2L by C to minus 2 into 1 minus R, right, minus 2 alpha of the cavity. Okay, this will be the answer, right. Now alpha of the cavity is nothing but alpha into L, okay, remember, okay. So tau p can also be given by 2 will get cancelled, right, we can take it out, L by C into okay, so there was a minus sign, no, here minus, so this minus and this minus will get cancelled, so we will end up with 1 minus R plus alpha into L, okay, this is the answer. Is it okay? So this is the way that we can derive tau p. Now there are two things, okay, in the absence of absorption, there is no absorption, okay, it is an empty cell. In case of an empty cell, gas cell, okay, where only R is there, reflectivity of the two resonating mirrors which are equal, so this, and no alpha cavity, no loss, then tau p is given by L by C into 1 minus R, correct, this is the way, right. And in case of a cell filled with some trace gas, okay, tau p is given by L divided by C to 1 minus R plus sigma at wavelength lambda into concentration into L, correct, because alpha is nothing but sigma into N, correct, absorption coefficient, okay, alpha is given by this, okay. So this is the way that, so there are two equations, equation 1 empty cell, equation 2 filled with, right, gas. So that seem this, so you can easily imagine, you can see this, that in the absence of losses, tau p cavity lifetime is given by this form, correct. In the presence of absorption, losses, the tau p value changes to this, it decreases by some amount. Okay. And so, what we measure is T transmission intensity pulse output from the resonating this cavity ring down right method. We will measure two decay characteristics, right, curves. One empty is that. Where tau p is given by L by C into 1 minus R, correct? And the filled cell where tau p, right, with the filled cell is given by L by C to 1 minus R plus sigma lambda to n into L, where L is the length of the cavity, it is given by this form. Okay. So, now we know these two outcomes, correct. From decay characteristics I can measure tau p, where intensity of the transmitted light intensity becomes 1 by E times its initial intensity, which will give me tau p. Tau p due to absorption loss is also can also be captured using this in the presence of gas molecules. What is the tau p? Now I know tau p this as well as this tau p. I know R, I know sigma lambda, I know length, I know C, I know L, everything. I can estimate n from here, isn't it? I can estimate n. Okay. So, this n is, it can be estimated by 1 upon C sigma lambda to 1 upon tau p, okay, minus 1 upon tau sorry, mt, okay, mt, I am writing in terms of mt here. Tau p, this is with the field, right, with the gas of space, can be estimated. It becomes very, see, and it can measure very small concentration. Okay, this approach, this is known as cavity ring down. Okay, ring down, right? It's based on absorption. Okay, there is nothing different, but it provides very small concentration. It is independent of the input intensity, even if due to the some laser intensity fluctuation, etc., even if the input intensity changes, does not matter, as far as I am capturing the output intensity with time and decay characteristics, I will be able to capture this, isn't it? Okay. So, it is independent of the fluctuation, intensity fluctuation, and measurement based on the lifetime we can estimate. Okay. However, if you can recall, the very important critical condition for such cavity ring down spectroscopy is length of the cavity should be maintained as n lambda by 2, correct. If the cavity length is not maintained, it will not be able to oscillate, the light inside the cavity will not be able to oscillate for long time because of the destructive interference and losses. We will end up with a very sudden decrease in the intensity, which can be a misinterpretation, right, which will end up with a misinterpretation, right. So, that should not happen. So, how to maintain such length, and you know what is lambda? It is in terms of micrometer, okay, the few hundreds of nanometer wavelength, it will be micrometer. Particularly gas species will have absorption, very large absorption in 2 micrometer wavelength range to 5 micrometer wavelength range, okay, which is also known as fingerprint area of most of the molecules. Okay. In that range, wavelength is, let us say, let us say 4 micrometer, or let us say long enough 5 micrometer is the absorption wavelength. So, L should be controlled within micrometer range. Okay. If there is a fluctuation due to vibration, and if the L changes in few micrometers range, the cavity ring down spectroscopy will not work. Okay. So, active control of this system is required. Hence, there are some challenges in terms of clinical applications, because in clinical surrounding ambience, even acoustic waves from external acoustic waves can also vibrate the mirror system, then the output will get affected. Okay. So, these are some of the challenges associated with cavity ring down spectroscopy. Okay. That is maintaining, controlling, active control of the cavity length, precise control of the cavity length becomes very important for us. However, many research groups are working for such control, etc. So, in fact, so now you understood cavity, how this part, this is what I explained to you, and this is the way cavity concentration can be estimated. Now, many research groups are working on this idea of cavity ring down spectroscopy based technique for estimating the concentration. Okay. So, I am not describing this inputs, etc., because I already told you that laser will come, a pulse laser goes through this cavity ring down cell, and it captures. We also need a reference, so which is also capture with the help of reference we can capture, and fast photo detector gives us the signal. Okay. And but the overall absorption technique is based on the absorption, correct, absorption of molecules. Okay. So, if the absorption is there, automatically we will be able to see the absorption transmission losses, and cavity ring down spectroscopy can allow us to capture. So, some research groups are also trying with breath sample and capturing this information, but in breath sample moisture also is present. Okay. So, moisture has to be removed, otherwise its absorption lines will interfere with some of the trace gas lines, absorption lines. So, there are ways of removing moisture from this sample and then capturing the information. Okay. So, there will be some cooling trap or moisture trap. So, we can feed the our human Excel through the some some type of what shall I say, collector, maybe a Tedlar bag, etc. It is that output is fed through the cooling trap. So, water will get trapped through the mass flow controller, so that exit volume, etc., is captured and fed into this absorption cell, and then absorption cell output in terms of transmission characteristics, in terms of cavity ring down measurements are being captured. Okay. So, for this purpose we can make use of such approach to measure acetone or ammonia or butane, carbon monoxide, H2O2, or dimethyl sulfide, NOx, or nitric oxide, methane, hexane, etc., etc. There are more than 2000 volatile organic compounds that can be captured, and some of them are acting as biomarkers, okay, for certain type of diseases. But you can see, I just want to bring to your notice that measurement of acetone does not mean that you have lung cancer. Okay. That is where the challenges are, to capture real information out of this. So, there are multiple biomarkers which will be used to capture this information. Okay. So, for example, for lung, butane is also captured, acetone is also captured, and then we can derive something. So, most of the ketones are related to diabetic activities, ammonia is related to renal disease or liver diseases, asthma, etc. So, these are we found out recently that ammonia is a very interesting right measurement, because related to liver diseases it can easily give us information about liver diseases, and acid ketones or acetones, acetone etc. are useful for diabetic conditions. So, acetone, other ketones etc. are useful for diabetic, capturing diabetic information. Right. So, this is one approach. Now, based on absorption spectroscopy, however, a slightly different approach is a photoacoustic spectroscopy. Okay. Which is also being considered very well, right, considered very, it's a very it's a potential application towards measurement or means towards biosensing or biophotonics, biosensing application. Okay. And it has emerged as a very good very good non-invasive approach for measuring trace gases, amount, trace gases, okay, concentration as well as photoacoustic imaging is possible using such technique. Okay. Now, see, important thing in case of the absorption, optical absorption based technique, if we try to use, okay, absorption based technique if we try to use, what we are using, input intensity of the light, which is let us say I0 lambda. What we are measuring? We measure transmitted intensity, correct. Now, if there are any tissue, other tissue molecules, if they start scattering the light, the transmitted intensity gets affected by two factors. One is absorption, of course, right, and the second one is scattering of the light. So, if I want to measure the transmitted intensity, I should know what is the amount of scattering which is coming into picture, otherwise it becomes difficult. In case of pulse oximetry, we could remove the factor of that scattering factor by using two wavelengths and taking ratio of this, right, and then eliminating the scattering factor, assuming that the scattering is approximately constant for both this wavelengths. Okay. So, which is constant. So, we could remove that factor very easily. However, sometimes this factor plays an important role. Okay, one aspect. So, scattering interferes with our measurement when we are measuring absorption based approach, directly optical absorption based. Secondly, signal to noise ratio, okay, is limited, it gets affected. Okay. Why? Because the transmitted intensity in the absence of any molecular absorption is going to be what? Whatever is the input intensity, okay, it will be very large. Now, if there are few molecules which are present, okay, which is going to absorb, which are going to absorb this light by small amount. So, what will happen? Transmitted intensity will decrease by small amount. So, your detector has to detect small change in the large amount of intensity, which is challenging, okay, which is challenging, right. Why? Because a small decrease against the noise signal of this existing light is very difficult to capture, right. So, for example, in this room this lots of tube lights are on. I have a detector here placed here somewhere and it is seeing. Now, one of the let us say tube light goes by small amount, it decreases, right. The detector may not be able to detect that small decrease. Why? Because already it is measuring very large intensity. In that small intensity decrease will be very challenging. Okay. But let us say this is a dark room, okay, and very small amount of light is let us say if one of the LED I switch on and light is emitted, the detector will immediately detect that light, right, because signal was 0, no, signal to noise ratio is quite large, right, while in the previous case where already there is a light intensity, signal to noise ratio with, right, is going to be quite small. Why? Because the absorption is quite less. If the absorption is significant and if light transmitted light intensity goes to 0, I can easily capture, okay, right. But if the absorption is so negligible, the small change in the light intensity is difficult to capture. So, signal to noise ratio becomes a very challenging task, okay, and that is why cavity ring down spectroscopy technique is used. So, that you do not measure such intensity, you rather measure the lifetime, okay, which can to certain extent it competes with the empty cell, right. So, to certain extent it is better, okay, if the absorption is there. However, the problem is in that case maintaining the cavity, right, time, etc. So, another aspect also related to this is if light has to transmit through various tissues, right, due to scattering, the light which is coming back, right, becomes so small. So, our detectors should be able to detect that small amount of light which is coming back, okay. If detector cannot detect, then also there is a right large this discrepancy in terms of signal to noise ratio. So, these are the factors to right to overcome this challenge. This challenge, a photoacoustic spectroscopy a technique is right can be used. So, in case of a photoacoustic spectroscopy technique, as name suggests, photons interact with the molecules to generate acoustic signal, okay, and these acoustic signals have a very less attenuation when they get transmitted. Not scattering is very small when they get transmitted through tissues, etc. So, the losses are reduced, okay. So, before we close, so of course, tomorrow means Wednesday evening I will explain you about this technique. However, we can say, let us say we are sending modulated light pulse in this gas cell, okay. So, modulated light pulses of certain intensity, they are being fed into this gas cell. Gas cell has many molecules, okay, and they will absorb this, let us say, light input pulse light. What will happen? The gas molecules will undergo transition, right, they will undergo transition, they will go to excited state, they will come back. When this process is happening, due to the molecular such vibration coming into picture, absorption coming into picture, localized heating comes into picture, okay, heating, right. It is because of the light absorption, molecules absorb this light, some amount of light which is getting absorbed and molecules gets excited, some of them may come back to the ground level with similar optical radiation, that we are not considering, but there will be some molecules which will come back through various other transitions to the ground level, and those transitions will generate a lot of heat, etc. So, that heating comes into picture. Now, if I am sending one pulse, the molecular, there are many n's molecules, their temperature will increase by small amount through this absorption, and if there is enough time between two pulses, this molecular temperature increase will again come back to ground state, and again the temperature will come to near room temperature. So, second pulse if I send, again heating, then cooling, heating, cooling. So, what happens, the molecules will undergo based on the pulse input heating, cooling, heating, cooling. Now, because of this heating and cooling, temperature is increasing, temperature is coming back to the initial temperature. When temperature increase takes place, if we use PV equal to nRT, right, normal ideal gas law equation, if temperature increases, pressure is going to accordingly increase. And if we see for a given constant cell with a constant volume etc., indirectly the density of this gas species changes, density or pressure wave is formed, pressure wave, because of the temperature increase decrease, the pressure wave is formed, because at high pressure then low pressure, as temperature increase decrease. So, because of this pressure wave formation, acoustic signal is generated. Okay. So, on off, pressure high, pressure low, pressure high, pressure low, it will generate acoustic waves. There is no acoustic waves in the absence of absorption, no acoustic waves are there, but in the presence of absorption of this input light intensity, acoustic waves are generated. Okay. So, if I can capture those signals using microphone, okay, so I use a laser with a particular wavelength corresponding to the absorption of the molecule, and modulated intensity, amplitude modulation or intensity modulation will end up with heating, cooling of this molecular here. Whenever light is present, heating, when light is absent, cooling, heating, cooling will generate acoustic waves. These acoustic waves will generate will be captured using microphone detection. This microphone output has a relationship with the concentration of the molecule. Okay. So, indirectly we are using light, but we are not capturing the absorption through light intensity measurement, but we are capturing the absorption through pressure waves or acoustic signals. Okay. And detecting the acoustic signal to capture and correlate it with the density or concentration of molecules. Okay. So, this effect has the advantage that background, assuming there is no external noise coming into picture, okay, that is our assumption. It is a challenging part, but assume that it is silent in the cell, then assuming that the background noise is constant or because of the external noise, but if in the absence of gas molecules, no acoustic signal, in the presence of gas molecule there is an acoustic signal. So, the signal to noise ratio is quite better. Over and above, it can also propagate, this acoustic waves can propagate through the tissue cells. So, the signal scattering, because of the acoustic signal scattering in the tissue is not there, and because of that you can capture the information efficiently using this photoacoustic technique. So, Wednesday we will try to capture, how can we make use of this photoacoustic signal towards some measurements for biophotonics. Is it okay? Okay, then thank you very much.